Before we can continue in our discussion of strength of materials, we have to understand some cross-sectional area properties, not just the magnitude of the area, but how that area is distributed and where's the balance point. The balance point is related to centroids, and how the area is distributed is related to the moment of inertia of the cross-sectional area. So let's consider it. The first thing we want to consider is just a centroid. You've probably dealt with centroids before. You may think of it as a balance point. It's the point where if you had the area laid out, cut out, imagine on a piece of cardboard, wherever you put your finger on that piece of cardboard to balance it, that would be the centroid. That would be the location of the balance point. Now, this is related very closely to something called the first area moment, or the first moment of the area. And really the first area moment tells you about an axis that goes through the centroid. So if you have a given area and it has an axis of symmetry, the centroid will lie on that axis. Now if it has two axes of symmetry, then the centroid will lie at the intersection of those two axes. And you can see that all 6 of these example shapes have 2 axes of symmetry, and so therefore the centroid lies at the intersection of those 2 axes. What about combined shapes? How do you find the centroid of a combined shape? Well, I've actually found the centroid of this combined shape. It's just a profile I drew in Solidworks, and we'll show you in another video how to use Solidworks to locate the centroid and other area properties as well. But for now, I want you to understand the concept. So I made this area and I broke it up into parts. Now think about the distance of this area from the vertical dotted axis. Okay, so we can break it up into 3 parts. Here's the first leg. You can see the centroid of that area. The second leg, there's the centroid of that area. And then finally the third leg and its centroid location. Now notice I move these out in the same way that the combined shape is distributed about this balance point, or this teeter-totter. So what are we really doing here? Well, what we're saying is that if I had a mirror image of this shape, even if it's broken up into multiple parts, these would balance, right? Basically the moment of each area individually would equal the moment of the total area. So that's what the equation says in the lower left-hand corner. It says that the moment of the combined area, in other words, the centroid distance y bar multiplied by the sum of all those individual areas. Well, it's all just one area here, but if we needed to find out what it was, we could just add up all 3 of the areas, right? That would be the moment of the shape on the right-hand side. That has to be equal to the moment of the individual areas that make up that shape, where we know the location of the centroid of each area times each individual area. So AIYI just means, for example, A1Y1 plus then A2Y2 plus A3Y3. That's why we have that summation there. And we're just saying these 2 balance. Now, that's not really what we're interested in. What we're interested in is rearranging the equation a little bit in order to locate y bar. It's pretty easy to find the sum of all the areas. It's also pretty easy to calculate the moment of each individual areas. But if we will add the moments of the individual areas and divide by the sum of the areas, then we have located the centroid of the combined area. And what we're really doing here is integration. You could take any arbitrary shape. You see this shape. Now, understand what I've done here is I've turned the thing on its side. Okay, so I've rotated it 90 degrees because that's usually how we think of this. So see the light blue shaded area. Pretend that's our shape. And we've got some functional curve, some shape of it. Well, in order to calculate the area moment of inertia for this area, what we'd have to do is multiply the distance to the differential area. You can see a little area there boxed off in white at that particular height. We'd have to take that differential area times the distance y from the x-axis up to the center of that area. Now, of course, when we're integrating, what we're really doing is allowing that area to go down to an area of 0, and adding up the moment of each of those infinitesimal areas, where we've got an infinite number of the infinitesimal areas. Now, the reason this is called the first moment of area is because look at the exponent on y in the integral. It's a 1, right? So that's the first moment of area, because you basically got a distance multiplied by an area. So that's a moment of an area. Now, all I've really done so far is I've found an axis. I haven't found the centroid yet, but I do know an axis where that centroid lies. So now what I have to do is consider the shape rotated 90 degrees and figure out where the centroid is in this case, right? So now I need to locate the centroid like this. It's 90 degrees from what it was before. And so now I need really all of these shapes, these areas. I need the moment of these areas from the axis that's rotated now, in order to figure out where the balance point is. And again, I've done this in Solidworks, so even though the right dimension is off the body a little bit, that's where the centroid is actually located. And hopefully this makes sense. Now, the reason I showed you this is for two purposes. Number one, you realize that this first moment of area only locates an axis that goes through the centroid. And so now what I'm doing in the past slide and this slide is I am locating the centroid based on two different lines relative to the figure, a horizontal and vertical line relative to the shape itself. But I also wanted to show you this, because it doesn't matter how those areas are arranged about the axis. All that matters is their distance from the axis, you see. So what I've shown on the left is just a rearrangement of the shape, and it will also balance the shape and help me find an axis to locate the centroid of this combined shape. Now there's another area moment. It's called the second moment of area. You may wonder why. Well, it turns out that all you're doing is changing the order on the distance. So this is a y squared. It's a second order or second moment of area. That's just what it's called. And it turns out that really the first moment of area is not useful in and of itself. In other words, it depends on how far from the axis I put the figure as to how large of an area moment I get. But for the second moment of area, we will be interested primarily in the second moment of area through the centroid, but we'll also be interested in the second moment of area through another point besides the centroid. So let's start off looking at this, and let's just imagine that we're taking the second moment of area through the centroid of the area. So we'll start there, because it turns out it's pretty easy to get the second moment of area through some point other than the centroid once you've got it through the centroid. So we're going to give this a name. We'll call it I, whereas we didn't give the first moment of area a name because we always just rearrange it to solve for the centroidal distance, since that's what we're trying to find from the first moment of area. But in the second moment of area, we're going to give it a name. We're going to call it I, and it's the second moment of area. So now understand, in this integration equation, what we would be doing is multiplying the square of the y distance from the axis times the area and adding it up, an infinite number of these across the entire figure. Now understand that our axis would actually have to go through the centroid of the area, and that's not what's drawn here. Now this can be a little bit of a challenge depending on the shape, and so at this point you should go to the back of your book, look up the appendix, and I think it's the first appendix or so, has a lot of different shapes and equations for letting you know the area, which is usually pretty easy, but also the second moment of area. Not only that, but they show you where the centroid is located for some very common simple shapes. And so this is something well worth knowing. You should definitely put a bookmark in your book on this appendix page because it's so valuable, and you just label it area properties or inertias or centroids or whatever will trigger your memory, so you go there to find area properties because they'll be so useful. So I'm not going to ask you to perform this integration. You can simply look it up. I will show you, like I said in another video, how to use Solidworks to find that second moment of area. Now remember that I said we were taking the second moment of area about an axis that passes through the centroid. What if we want the second moment of area of an area about an axis other than one that goes through the centroid? Well, in that case, there's something called the parallel axis theorem. I won't prove it to you, but it's actually really simple. All you really have to do is take the second moment of inertia through the centroid and add to it the area times the distance between the axis going through the centroid and the axis that you're interested in. Now I've got a summation here because if you've got a body that consists of a couple of different areas, like that one I showed a minute ago, that funny chair looking thing that's consisted of 3 areas, well in that case, to calculate the total area moment of inertia about some other axis, you can use this equation, just add them all up. They're linear, they just add together. So you do this for area 1, 2, and 3 that I showed you before about whatever axis you want. And you'll see more of this in more details in the example problems I work for you. Now this can get pretty involved very quickly. And so I've actually put together a spreadsheet for you that I'll again demonstrate in the example problems that will help you locate the centroid and also the area moment of inertia for a particular shape. And so I'll show you some tricks in how to use this, and it turns out you can deal with positive and negative areas as well, and use the spreadsheet to calculate moments of inertia and centroids and so forth of fairly complicated combined areas. Now, another type of cross-sectional area that we're interested in are standard shapes. So if you go down to a metal supply store and you buy an I-beam, for example, yeah, it basically looks like 3 separate areas, but there's a lot of detail, there's a lot of rounded corners, and you really don't have 3 separate perfect rectangles connected together. Really, it's a little more complicated. And so for wide flanges and other flanges, which are I-beams, S-shapes I believe they're called, for many different cross-sections of standard available steel and aluminum, in the back of your book there are area properties, the second moment of area, the centroid location, all those things, and they're very, very handy. We will use them extensively, so make sure you mark those pages in your book because they're very, very useful, and you'll probably want to mark all of these pages with their own tab. Another property that you will see in the back of the book is something called a radius of gyration, and that's just a relationship between well, it's a computation based on the second moment of area and the area itself, and you can see the equation here. Those always relate to each other this way, so sometimes it's more convenient to use the radius of gyration in equations, and that's why it's defined. So I will show you in Solidworks how to locate a centroid and also how to calculate the second moment of area in Solidworks. Now it turns out that Solidworks will actually give you a couple of different second moments of area. I don't know if you can see this on the video, but under the section properties there's an IX and an IY that are listed. And basically all you really do is you draw the area that you want, sketch it, extrude it a little bit, and instead of going to evaluate and clicking the mass properties, which is what most students accidentally do, rather what you do is you click the particular area that you want area properties for, and you click the button for section properties.